In mathematical physics, Minkowski space or Minkowski spacetime is a combination of Euclidean space and time into a four-dimensional manifold where the spacetime interval between any two events is independent of the inertial frame of reference in which they are recorded. Although initially developed by mathematician Hermann Minkowski for Maxwell's equations of electromagnetism, the mathematical structure of Minkowski spacetime was shown to be an immediate consequence of the postulates of special relativity. Minkowski space is closely associated with Einstein's theory of special relativity, and is the most common mathematical structure on which special relativity is formulated. While the individual components in Euclidean space and time will often differ due to length contraction and time dilation, in Minkowski spacetime, all frames of reference will agree on the total distance in spacetime between events. Because it treats time differently than the three spatial dimensions, Minkowski space differs from four-dimensional Euclidean space. In Euclidean space, the isometry group is the Euclidean group, the analogous isometry group for Minkowski space, preserving intervals of space-time equipped with the associated non-positive definite bilinear form is the Poincare group. The Minkowski inner product is defined as to yield the spacetime interval between two events when given their coordinate difference vector as argument. History: four-dimensional Euclidean spacetime in 1905, and later published in 1906. Henry Poincare showed that, by taking time to be an imaginary fourth spacetime coordinate, a Lorentz transformation can be regarded as a rotation of coordinates in a four-dimensional Euclidean space with three real coordinates representing space, and one imaginary coordinate, representing time, as the fourth dimension. Since the space is then a pseudo-Euclidean space, the rotation is a representation of a hyperbolic rotation. Although Poincare did not give this interpretation, his purpose being only to explain the Lorentz transformation in terms of the familiar Euclidean rotation, the idea was elaborated by Hermann Minkowski, who used it to restate the Maxwell equations in four dimensions, showing directly their invariance under the Lorentz transformation. He further reformulated in four dimensions the then-recent theory of special relativity of Einstein. From this he concluded that time and space should be treated equally, and so arose his concept of events taking place in a unified four-dimensional space-time continuum. Minkowski space in a further development, he gave an alternative formulation of this idea that used a real-time coordinate instead of an imaginary one, representing the four variables of space and time in coordinate form in a four-dimensional affine space. Points in this space correspond to events in spacetime. In this space, there is a defined light cone associated with each point, and events not on the light cone are classified by their relation to the apex as space-like or time-like. It is principally this view of space-time that is current nowadays, although the older view involving imaginary time has also influenced special relativity. Minkowski, aware of the fundamental restatement of the theory which he had made, said, "The views of space and time which I wish to lay before you have sprung from the soil of experimental physics, and therein lies their strength. They are radical. Henceforth space by itself, and time by itself, are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." Hermann Minkowski, 1907. For further historical information see references Galison, Corey and Walter. Mathematical structure. For an overview, Minkowski space is a four-dimensional real vector space equipped with a non-degenerate, symmetric bilinear form on the tangent space at each point in spacetime, here simply called the Minkowski inner product, with signature either/or. In practice, one need not be concerned with the tangent spaces. The vector space nature of Minkowski space allows for the canonical identification of vectors in tangent spaces at points with vectors in Minkowski space itself. For some purposes it is desirable to identify tangent vectors at a point P with displacement vectors at P, which is, of course, admissible by essentially the same canonical identification. The signature refers to which sign the Minkowski inner product yields when given space and time basis vectors as arguments. In general, mathematicians and general relativists prefer the former, while particle physicists tend to use the latter. Arguments for the former include continuity, from the Euclidean case corresponding to the non-relativistic limits C infinity. Arguments for the latter include that otherwise ubiquitous minus signs in particle physics go away. Mathematically associated to this bilinear form is a tensor of type at each point in spacetime, called the Minkowski metric. The Minkowski metric, the bilinear form, and the Minkowski inner product are actually all the very same object. In coordinates, this is the 4 times 4 matrix representing the bilinear form. Keeping this in mind may facilitate reading what follows. For comparison, in general relativity, a Lorentzian manifold L is likewise equipped with a metric tensor G, which is a non-degenerate symmetric bilinear form on the tangent space TPL at each point P of L. In coordinates, it may be represented by a 4 times 4 matrix depending on space-time position. Minkowski space is thus a comparatively simple special case of a Lorentzian manifold. Its metric tensor, called the Minkowski metric, is in coordinates the same symmetric matrix at every point of M, and its arguments can, per above, be taken as vectors in spacetime itself. Introducing more terminology, Minkowski space is thus a pseudo-Euclidean space with total dimension n equals 4 and signature or elements of Minkowski space are called events. Minkowski space is often denoted R3, 1 or R1, 3 to emphasize the chosen signature, or just M. It is perhaps the simplest example of a pseudo-Riemannian manifold. Pseudo-Euclidean metric generalities. The Minkowski metric eta is the metric tensor of Minkowski space. It is a pseudo-Euclidean metric. As such, it is a non-degenerate symmetric bilinear form, a type tensor. It accepts 2 arguments sup, Vp, vectors in Tpm, Pm, the tangent space at P and M. Due to the above-mentioned canonical identification of Tpm with M itself, it accepts arguments U, V with both U and V and M. As a notational convention, vectors V and M, called 4 vectors, are denoted in sans serif italics, and not, as is common in the Euclidean setting, with boldface V. The latter is generally reserved for the 3-vector part of a 4-vector. The definition yields an inner product-like structure on M, previously and also henceforth called the Minkowski inner product, similar to the Euclidean inner product, but it describes a different geometry. It has the following properties. The first 2 conditions imply bilinearity. The defining difference between a pseudo-inner product and an inner product proper is that the former is not required to be positive definite. That is, eta less than 0 is allowed. 2 vectors v and w are said to be orthogonal if eta equals 0. A vector E is called a unit vector if eta equals plus or minus 1. A basis for M consisting of mutually orthogonal unit vectors is called an orthonormal basis. For a given inertial frame, an orthonormal basis in space, combined by the unit time vector, forms an orthonormal basis in Minkowski space. The number of positive and negative unit vectors in any such basis is a fixed pair of numbers, equal to the signature of the bilinear form associated with the inner product. This is Sylvester's law of inertia. More terminology. The Minkowski metric is a pseudo-Riemannian metric, more specifically, a Lorentzian metric, even more specifically, the Lorentz metric, reserved for 4-dimensional flat spacetime, with the remaining ambiguity only being the signature convention. Minkowski metric. From the 2 postulates of special relativity follows that the spacetime interval between 2 events 1, 2, is independent of the inertial frame chosen. The factor plus or minus simply means that the choice of signature is left open. The numerical values of eta, viewed as a matrix representing the Minkowski inner product, follow from the theory of bilinear forms. Just as the signature of the metric is differently defined in the literature, this quantity is not consistently named. The interval is sometimes referred to as the interval squared. Even the square root of the present interval occurs. When signature and interval are fixed, ambiguity still remains as which coordinate is the time coordinate. It may be the fourth, or it may be the 0th. This is not an exhaustive list of notational inconsistencies. It is a fact of life that one has to check out the definitions first thing when one consults the relativity literature. The invariance of the interval under coordinate transformations between inertial frames follows from the invariance of, provided the transformations are linear. This quadratic form can be used to define a bilinear form via the polarization identity. This bilinear form can in turn be written as where eta is a 4 times 4 matrix associated with eta. Possibly confusingly, denote eta with just eta as is common practice. The matrices read off from the explicit bilinear form as in the bilinear form with which this section started by assuming its existence is now identified. For definiteness and shorter presentation, the signature is adopted below. The choice has no physical implications. The symmetry group preserving the bilinear form with one choice of signature is isomorphic with the symmetry group preserving the other choice of signature. This means that both choices are in accord with the two postulates of relativity. Standard basis. A standard basis for Minkowski space is a set of 4 mutually orthogonal vectors E0, E1, E2, E3, such that these conditions can be written compactly in the form relative to a standard basis. The components of a vector V are written where the Einstein notation is used to write V equals V mu E mu. The component V0 is called the time-like component of V, while the other 3 components are called the spatial components. The spatial components of a 4-vector V may be identified with a 3-vector V equals. In terms of components, the Minkowski inner product between two vectors V and W is given by, and here lowering of an index with the metric was used. Technically, a non-degenerate bilinear form provides a map between a vector space and its dual. In this context, the map is between the tangent spaces of M and the cotangent spaces of M. At a point in M, the tangent and cotangent spaces are dual. Just as an authentic inner product on a vector space with one argument fixed by Rie's representation theorem may be expressed as the action of a linear functional on the vector space, the same holds for the Minkowski inner products of Minkowski space. Thus, if V mu are the components of a vector in a tangent space, then eta mu nu V mu equals V nu are the components of a vector in the cotangent space. Due to the identification of vectors in tangent spaces with vectors in M itself, this is mostly ignored, and vectors with lower indices are referred to as covariant vectors. In this latter interpretation, the covariant vectors are identified with vectors in the dual of Minkowski space. The ones with upper indices are contravariant vectors. In the same fashion, the inverse of the map from tangent to cotangent spaces, explicitly given by the inverse of eta in matrix representation, can be used to define raising of an index. The components of this inverse are denoted eta mu nu. It happens that eta mu nu equals eta mu nu. These maps between a vector space and its dual can be denoted eta flat and eta sharp by the musical analogy. The time-proven robustness of the formalism itself, sometimes referred to as index gymnastics, ensures that moving vectors around and changing from contravariant to covariant vectors and vice versa is mathematically sound. Incorrect expressions tend to reveal themselves quickly. Geometry, Lorentz transformations and symmetry. The Poincare group is the group of all transformations preserving the interval. The interval is quite easily seen to be preserved by the translation group in 4 dimensions. The other transformations are those that preserve the interval and leave the origin fixed. Given the bilinear form associated with the Minkowski metric, the appropriate group follows directly from the theory of classical groups. In the linked article, one should identify eta with the matrix phi. The appropriate group is O, in this context called the Lorentz group. Its elements are called Lorentz transformations. For other methods of derivation, with a more physical twist, see derivations of the Lorentz transformations. Among the simplest Lorentz transformations is a Lorentz boost. For reference, a boost in the x direction is given by where is the Lorentz factor, and other Lorentz transformations are pure rotations, and hence elements of the SO subgroup of O. A general homogeneous Lorentz transformation is a product of a pure boost and a pure rotation. An inhomogeneous Lorentz transformation is a homogeneous transformation followed by a translation in space and time. Special transformations are those that invert the space coordinates and time coordinate respectively, or both. All four vectors in Minkowski space transform, by definition, according to the same formula under Lorentz transformations. Minkowski diagrams illustrate Lorentz transformations. Causal structure. Vectors V are classified according to the sign of C2 T2 R2. A vector is time-like if C2 T2 greater than R2, space-like if C2 T2 less than R2, and null or lie-like if C2 T2 equals R2. This can be expressed in terms of the sign of eta as well, but depends on the signature. The classification of any vector will be the same in all frames of reference, because of the invariance of the interval. The set of all null vectors at an event of Minkowski space constitutes the light cone of that event. Given a time-like vector v, there is a world-linear of constant velocity associated with it, represented by a straight line in a Minkowski diagram. Once a direction of time is chosen, time-like and null vectors can be further decomposed into various classes. For time-like vectors one has future-directed time-like vectors whose first component is positive, and past-directed time-like vectors whose first component is negative. Null vectors fall into three classes. The zero vector, whose components in any basis are future-directed null vectors whose first component is positive, and past-directed null vectors whose first component is negative. Space-like vectors are in elsewhere. The terminology stems from the fact that space-like separated events are connected by vectors requiring faster than light travel, and so cannot possibly influence each other. Together with space-like and light-like vectors there are 7 classes in all. An orthonormal basis for Minkowski space necessarily consists of 1 time-like and 3 space-like unit vectors. If one wishes to work with non-orthonormal bases, it is possible to have other combinations of vectors. For example, one can easily construct a basis consisting entirely of null vectors, called a null basis, over the rails. If 2 null vectors are orthogonal, then they must be proportional. However, allowing complex numbers, one can obtain a null tetrad, which is a basis consisting of null vectors, some of which are orthogonal to each other. Vector fields are called time-like, space-like or null if the associated vectors are time-like, space-like or null at each point where the field is defined. Chronological and causality relations. Let x, y, m. We say that x chronologically precedes y if y minus x is future-directed time-like. This relation has the transitive property and so can be written x less than y. X causally precedes y if y minus x is future-directed null or future-directed time-like. It gives a partial ordering of spacetime and so can be written xy. Reverse triangle inequality. If v and w are both future-directed time-like for vectors, then in the sign convention for norm relationships to other formulations. Different number of dimensions. Strictly speaking, Minkowski space refers to a mathematical formulation in 4 dimensions. However, the mathematics can easily be extended or simplified to create an analogous Minkowski space in any number of dimensions. If n2, n-dimensional Minkowski space is a vector space of real dimension n on which there is a constant Lorentz metric of signature, or these generalizations are used in theories where spacetime is assumed to have more or less than 4 dimensions. String theory and M-theory are two examples where n greater than 4. In string theory, there appears conformal field theories with 1 plus 1 spacetime dimensions. Flat versus curved space. As a flat spacetime, the three spatial components of Minkowski spacetime always obey the Pythagorean theorem. Minkowski space is a suitable basis for special relativity, a good description of physical systems over finite distances in systems without significant gravitation. However, in order to take gravity into account, physicists use the theory of general relativity, which is formulated in the mathematics of a non-Euclidean geometry. When this geometry is used as a model of physical space, it is known as curved space. Even in curved space, Minkowski space is still a good description in an infinitesimal region surrounding any point. More abstractly, we say that in the presence of gravity spacetime is described by a curved four-dimensional manifold for which the tangent space to any point is a four-dimensional Minkowski space. Thus, the structure of Minkowski space is still essential in the description of general relativity.